We have been discussing the factors influencing the variation of acceleration due to gravity on the Earth. In this connection, we have considered the shape of the Earth. There we have seen that the Earth is not perfectly spherical, it is ellipsoidal with a bulge at the equator and flattening at the poles. Due to that, there is some decrease in the acceleration due to gravity at the equator when compared to the poles. After that, we have considered the rotation of the Earth. There we have seen that the Earth is rotating about its axis from west to east. Due to its rotation, all the bodies present on its surface, they revolve in different circles but with the same angular velocity. Due to their rotation, there is some centrifugal force which acts away from the center, or there is some centrifugal acceleration acting against the acceleration due to gravity. As a result, there is some decrease in the value of g. This decrease is found to be different at different positions depending on the latitude of the place. The maximum decrease in the acceleration due to gravity is at the equator, and that is equal to r omega square, that is 0.034 meter per second square. The effect of rotation is nil at the poles. So whether they are to rotate faster or slower, there is no effect at the poles. But at all places, there is some effect. Out of this, the effect is maximum at the equator and minimum at the poles. After that, we have considered the effect of height. There we have seen that as you move away from the surface of the Earth, the effective distance from the center of the Earth increases and the acceleration due to gravity decreases. Now if you go deep into the Earth, this thing will make us think that perhaps as we move deep into the Earth, we are getting closer to the center of the Earth, the effective distance is decreasing, so acceleration due to gravity should increase. But in reality, if you go deep into the Earth, then also the acceleration due to gravity decreases. That means from the surface of the Earth, as you go above or below, in both the cases, the acceleration due to gravity decreases. As we go above, we have got a formula, gh is equal to g bracket r by r plus h whole square. Then what is the respective formula in the case when we go deep into the Earth? At the surface of the Earth, the acceleration due to gravity is given by two formulae. One is g is equal to gm by r square, and the other is 4 by 3 pi g rho r. This gm by r square, it is valid for all distances from r to infinity. That means for all the points outside the Earth. Starting from the surface to any point outside the Earth, this is valid, and in this case the mass of the Earth is constant. If you go deep into the Earth, the mass of the Earth is not constant. For example, if you are at a depth d, you can see that only this mass is effective. The mass of the shaded portion is effective, not the mass of the whole Earth is effective. So here in this case the mass is variable, therefore this formula gm by r square cannot be used. Then we have to use a formula which contains some quantity which is remaining constant. The other formula is 4 by 3 pi g rho r. Here rho is supposed to be constant, but in fact even rho is also not constant. As we go deeper into the Earth, the density of the Earth increases. To make the thing simple, let us suppose that rho is constant. Then we can use this formula 4 by 3 pi g rho r. This formula is valid for all values of r, that is distances ranging from 0, that is from the center of the Earth to the surface of the Earth. Let us consider a point at a depth d from the surface. Then its effective distance from the center, small r, is equal to r minus d. The acceleration due to gravity at a depth d is given as gd is equal to. There we have written g is equal to 4 by 3 pi g rho r. Now here gd is equal to 4 by 3 pi g rho into r minus d. Dividing equation 2 by equation 1, we get gd by g is equal to r minus d by r, or gd is equal to g into r minus d by r. gt is equal to g into r minus d by r, or g bracket 1 minus d by r. This formula, it reminds us of one more formula which we have considered in the case of height. There it was gh is equal to g bracket 1 minus 2h by r. But that formula is valid only for heights very much small when compared to the radius of the earth, whereas this formula is valid for all distances ranging from 0 to r. These are the limits for this formula. There the limits was that h should be as much small as possible when compared to the radius of the earth. Smaller the value of h, more accurate will be the answer. Now let us consider this table. Before we consider this, let us see that the weight of a body, it depends on the acceleration due to gravity. If acceleration due to gravity becomes half at any place, the weight of a body also becomes half. Mass does not change, but the weight changes. Now, if we take a simple pendulum to different depths, the acceleration due to gravity changes. We know that the time period of a simple pendulum is given by 2 pi under root L by g. As g changes, time period also changes. We know that the time period at the surface t is equal to 2 pi under root L by g. The time period at a depth t dash is equal to 2 pi under root L by gd. Then on dividing this by this, we get t dash by t is equal to 2 pi will get cancelled, L will get cancelled, it will be under root g by gd. Under root g by gd. This under root g by gt is equal to r by r minus d. So the effective time period at a depth d can be easily obtained by substituting in this formula: radius of the earth and the depth of the place. Now let us consider this table. First we are considering a point at the surface. So depth is 0. And what is the distance from the center? It is r. Acceleration due to gravity g. Weight of a body is w. The time period of a simple pendulum is t. These are the starting points. Now we are going deep. Suppose we are at a depth r by 4. Then remaining distance is 3r by 4. The acceleration due to gravity and the weight, they will be proportional to the remaining distance. Since the remaining distance is 3/4, acceleration due to gravity is also 3/4, weight also becomes 3/4. What about the time period? For time period t is equal to r by 3/4 r. So r will get cancelled, 3/4 will become under root 4 by 3, that will be 2 by root 3. So the time period is 2t by root 3. Now let us go further deeper at this depth r by 2. So the remaining distance is also r by 2. Since the remaining distance is r by 2, acceleration due to gravity is g by 2. Effective weight is also becoming w by 2. What about the time period? T dash is equal to t bracket under root r by 2. R will get cancelled. 2 will go to the numerator, so it will become t root 2. Suppose we go further deep. The depth is 3r by 4. Then the remaining distance is r by 4. The acceleration due to gravity is g by 4. Effective weight is w by 4. Time period t dash is equal to t under root r by 4. R will get cancelled. 4 will go to the numerator. 4 under root is 2. So it will be 2t. Suppose we go further deeper to a depth r. Then what is that? Means we are at the center. What is the distance from the center? 0. Since distance from the center is 0, weight of acceleration due to gravity becomes 0. Weight will also become 0. What about the time period? T dash is equal to t bracket under root r by 0, that is infinity. Then let us consider one more thing. Suppose we are at a depth 36% r. So remaining distance is 64% r. Since the remaining distance is 64%, the acceleration due to gravity is also 64%. Weight will also be 64%. What about the time period? T dash is equal to t bracket under root 100 by 64. That is 10 by 8. That is 5 by 4. So the time period will be 5t by 4. Suppose we are considering at a depth 64% r. Then the distance from the center of the earth is 36% r. The acceleration due to gravity will become 36% g, and the weight will also become 36% g. Then t dash is equal to under root r by 36% r. R will get cancelled. 36% will become 100 by 36 under root, that is 10 by 6. 10 by 6 means 5 by 3. So the time period at the depth is equal to 5t by 3. I hope you understood this. Okay, after this we'll take some more problems.